Very good afternoon, all. Welcome to the class, and let's continue talking further on binary trees. Last time we have already discussed binary tree creation. Some improvements in the creation itself we have discussed and suggested by making double star, as well as create three where meaningful message could be given. And we last time targeted to implement a copy a binary tree, and I have given you a homework for trying to find max out of a binary tree and the count of nodes. So I'm sure some of you have attempted this, and some of you have got good idea, but some of you might be not very clear how recursively these things can be done. So today we are going to clearly understand how most of these will be implemented and how most of these can be recursive, and recursion implementation, how to think of. So primarily in this case, the recursive process of working we will understand via an example. Let's say I want to have a find max. So find max function to be written, that will mean how to implement, of course, what will be the function's first header. Find max function to be implemented. The parameters to this, obviously the binary tree root. So node star root will be passed. What it will return? It will return some int value, the maximum out of the tree. For the time being, if I assume all positive values, so we can assume that accordingly maximum will be out of these all values are the positive. If they are negative also, accordingly we can revise that. So now out of this tree, I have to find max. So effectively, the first thing is, can you make a recursive definition out of this find max? Recursive definition, if you are able to think of find max, that will effectively mean that recursively apply the same function on left subtree as well as on right subtree. If you are able to think some definition how to find max using this left subtree recursion and right subtree recursion, probably the work will be over. So how to do this? Effectively, the rule for this is, will this be a sub-step in solving this problem? If yes, obviously recursion is applicable. So if you can say that finding max from the left subtree and right subtree can be useful to find overall the find max. If yes, means recursion is useful. Recursive solution will be easy and straightforward. If not, then obviously you have to think of something else. What does that mean? Effectively, if it is possible, this will also mean that focus will be on current root only. That will be the advantage of doing this. So understanding recursion requires a more careful visualization and planning. So this will become clear once I discuss so many operations today, all using recursion, and you will have more clarity and vision to plan these things. First time you might not be able to think that how easily this could be done by me, and why you are not able to think doesn't matter. I have practiced a lot and I have been using this for many years, so the clarity is with me. The same clarity will come with you also within certain time. Find max. So if I say recursion is visible, then always what you have to do. Say currently you have root. Let's say this value is 30. Then now if you see recursion visible, forget about the rest of the tree. Consider it as a left subtree. That's it. Don't draw anything. Don't bother about anything. Consider this side to have some right subtree. First thing. So this is first way to do this. If you have done this, now think that how my find max will be useful. We have said that find max will be able to work on this side also. Find max will be able to work this side also. What it will do? This process will return something that I can claim that will become a left max. This side will return something, and this value I will say let it be called as a right max. So recursion if applied, now you assume that you have found left max and right max correctly. You assume always. Recursion, you always assume that left max and right max are computed correctly. So that effectively means from left side, let's say the maximum was found and the tree which we have drawn last time, probably there 70 was the highest. So I will get 70 as the maximum value from this side. This side we have drawn the last time the tree. So for that 100 was the highest. So let's assume this max is able to find 100 as highest. Now, knowing this, and these are only one line calls. So knowing this and assuming this to be working correctly, what is now right your find max? What is the value for this function? How will you get max out of this? So max out of this is obviously 100. How? You will say effectively you have to find maximum out of 30, which was the roots data, 70 and 100. What is 30? Root arrow data. What is 70? Left side max. Max of left subtree. And similarly, this also from the right subtree. So out of this, you are able to easily find, let me just have this glowing. Yeah. So out of this, we are easily able to have maximum found, and that will be the logic. So what I say is, now you are not bothered how 70 came, how 100 came, assume it came correctly. Can you find the correct value? This becomes effectively recursive definition. So I say, find max recursively applicable how? If the tree exists, it is effectively maximum out of what? Root arrow data, out of find max on the left side, and find max of right subtree. Let me just have page readjusted. So out of these three values, I have this. When this was applicable, if root was not null, and if root is null, then what is the maximum? For example, at any point, I say currently my root is null. What is now maximum? Root null means neither it has left subtree nor right subtree nor root existing. Effectively, max doesn't exist. Non-existing. Because there is no value in the tree. Non-existing max effectively means we will assume, let's say -1 because it is non-existing value. So non-existing value will be returned. So -1 must not exist in the tree, obviously, must not be a valid value in the tree. That value will assume to be returned. For example, if you wanted find max out of a big array, initially you assume some -infinity to be the maximum. So this is -infinity being returned, and if you find a better value, obviously. So this value should be the smallest or smaller than the smallest possible value. So -infinity you can use if tree had negative values also. We assumed a tree had no negative values. If I say that a tree can have negative values also, then we will assume this to be minus infinity. Of course, minus infinity on computer won't exist. So we will assume the minimum int value or and the negative value, smallest value of the integer, and that can be reserved to be used. Now, that straight away becomes the implementation. Implementation now will be very easy. You can easily say int find max, node star root. So first assumption is that if tree was not null, if a tree had some useful data, try to find the recursive definition. Once you have thought of recursive definition, recursion is always conditional. Recursive calls must be always conditional. Hence, condition you have to think of, and condition mostly will mean if the tree has become empty, if the root is empty. So you can put that as a condition initially itself. If a root equal to null, let's say. This means tree is empty. Tree has nothing. So you could say return -1 or minus infinity in general. Or you could say in this case, I could return -1 in this case. But minus infinity, of course, you can return theoretically. And instead of infinity, you can have some suitable value. Else. Whether you write else or you don't write else, one and the same thing. So writing else might be useful. If you want to write else, you can put bracket. Even if you don't write, still it means automatically else. So else is automatic because return executed will stop. Otherwise, this is automatically written. Now what to do? I have to find effectively maximum from the left subtree. So assume that now I am focusing only on the current root and its trees on the both sides. That's it. No further details to be bothered. From the left subtree, I will say I will find a left max. So I can have some int variable taken, and this will receive find max from the left side. Root arrow left. Similarly, right max to be found from the right subtree. And what? So now I have these two values and I have one root's value because root is also not null. Some of these could be null, left side could be null, right side could be null. When recursion will happen, at that time it will be checked. And if at that time that left side was null, the termination will happen automatically. If right side was null, that will happen. If both had certain values, accordingly the code will proceed and get some max value. Don't bother how it will do. If I have written correctly for the current node, guaranteedly it will work correctly for the other nodes and recursively on full subtree also. So that's the beauty of recursion. So now I can say, okay, I can compare these two. So I can say, fine, I can compare if left max is greater than right max. So then I can say current max or some max I can take. So I can say max equal to left max. Out of this else, I can say max equal to right max. So out of these two, the max has been found. And once max has been found, now I can compare max with root arrow data. So if root arrow data is greater than max, then my overall max is root arrow data. Otherwise, so I can, in this case, what I have to return? Root arrow data. Else what I will return? Else obviously the max is highest, so return max. So that way I can easily write. So assuming this call worked well, assuming second call also worked well, and everything is ready, and then I could do easily this. Straight away simple. Now, that's why I said take minus infinity, because at some stage, this recursion will terminate by going to the root becoming null. That time I should return the value which is smaller than the smallest, so that it, when compared with either left max or right max or with the root, anyone compared with that time, minus infinity will never create a problem. If we talked of all positive values, then -1 will not create a problem and it will work smoothly. So this is how effectively you have to always think. Talking of this similar process, now it will be much more easier to think and find a count. Let's say I want to count. So count will obviously mean I will have a function to return int. Root will be passed because count should tell me how many counts. So node star root will be passed. So again, step 1, assume a valid tree, not null, valid binary tree, and find whether recursion will be useful or not. Whether recursion will be applicable or useful or not. How to find? Think that if it is applied on the left subtree and that counts the subtrees of the left subtree. So I have current root, some data, let's say 30. I say this recursion applied tells number of nodes. Let's say this side I have 4 nodes. This recursion applied on the right subtree and this tells the total numbers are 3. So 4 nodes from the left subtree, right? 3 nodes from the right subtree. Now this information is useful to find overall count? Yes. So it says, if yes, so I'll say go for step 2. Make recursive definition. So you should be able to define count as a recursive definition. Once you are able to do recursive definition finding, then finally step 3 will be simple. What is the stopping criteria or non-recursive step? And find out that and then coding of that. Coding to be done. Assuming your recursion left side on the right and on the right side works always correct. And right subtree works perfect. Assume this and don't bother how it will happen, then you can easily do that coding. So I have seen it is recursively useful, so I will say recursive definition. So what is count? Count on a root, how it should be computed. Count on some binary tree root 1 or whatever you have. If the tree exists, what is the count? Count of the left subtree, obviously, of left subtree. That will give me 1 count, plus count of the right subtree. So this has given me 4, this has given me 3. Don't bother. Assume now I am focusing only on the root node. Focus on current root only. Because left subtree is solved already now. Right subtree is solved. This has done. This recursion has solved full left subtree and told me 4 somehow. This also told me 3 somehow. What is my total count? 4 plus 3 plus 1. This root is also there. So I will say count of this plus count of this plus 1. So I'll just say this statement is outside. So effectively my count is nothing but left count plus right count plus 1. Stopping criteria, step 3, you can easily find. If a tree is null, root equal to null is the obvious stopping criteria. If root is null, what is the count? What will be the count? Obviously 0. So I will say that will be the return 0 in this case. And that's it, done. Now step 4, let's do the coding. So effectively I will say int count, whatever parameters to be written. Do this. If root equal to null, remember always if it is int, every recursive call must be returning something and that value must be used. If root is null, then also what we will return. Return you should not forget. 0, because no node exists. Count means this. Else, recursive definition applied. So let's count left count from the left subtree. Count on the left applied on the left side. Recursive definition. Assume this works and you got left count working. If you have got this left count working, your focus on this side is no more needed. It is ready. So this side's count is ready. Apply the same logic again. Right count. Count right side. Applied. Count found. This side count ready. Now, ready means effectively you are having here some root node. This side count is ready. Count equal to 4. This side count equal to 3 or any value. But something is ready on both sides. Whatever was the actual count, that count is ready. Once you have that count ready, effectively 4 means effectively some variable left count is ready. Similarly, this right count is ready. What is the total count? Total count is my simple 1 for the root, plus this count, plus this count. So I can simply say return 1 plus left count plus right count. So this is the simple logic you could easily do. So this must be both will be obviously of int data type because I am returning int, and accordingly you can have the overall return value. Recursively, automatically this will go recursively and at some point root will become null, that will automatically this. So you should be able to visualize how it grows. How recursion is solving. Ultimately, for example, I said here 30, here I have 40, here you had 50, here you had 60, for 60 you had, let's say 70, like this. This side you had 80, then you had 90, and let's say this side you had 100, whatever way you have made. So this side count I said 4, how did it come? From 30, call will go to the left side, left count for this tree to be generated. On this tree again count to be generated, it will say this count is also equal to count on the left side plus count on the right side. Count on the left side will go to this call. It will say count of 1 plus count on the left side, count on the right side. This side count will come as 0. So this side left count ultimately will come as 0 because the node will become null. It will return 0. This side's right count will also come as 0. So for this root, the count will become 1 plus 0 plus 0. For this node, count comes now first time 1 plus 0 plus 0 returned. This overall becomes the left side count. Similarly, right count will come this side. For this node, count will be attempted. Recursion will reach to the 70. For 70, recursion will be attempted. 70 will say left side 0, right side 0, 1 plus 0 plus 0. This will become 1 here. This will say count is the left count 1, root itself 1, left side 1, right side 0. It will return 2. And accordingly, now I reach here. This count 40 will return 1 for the root, left side count to be 1, right side count to be 2. So this 1 being used, this 2 being used, this overall becomes 4. Similarly, from this side, it will come as 3, and then this will return 1 plus 4 plus 3. And this is how my overall count will be computed and processed. Having understood this, I'm sure now you can easily make similar logics. So now I'll be going much more easily for various other operations. For example, I say find height of a tree. So height of a tree means what? It is effectively the highest level of a node, any node in the tree. So height of the tree effectively I have to find. Highest level of a node, we have already decided. Any node. And level means what? Root is at level 1. And other nodes have similarly level 2, 3, and so on. Next at level 2, or its children, roots children are at level 2. Further children at level 3, and so on. So recursion useful or not? Means on a certain node I am 30. If I find this side's height, this side's height found. Assume these heights are found. Now can recursion solve to find overall height? Yes. So if yes, recursive definition to be made. So height of a tree will be equal to what? I say height of the tree is now obviously 1 plus either this height or this height. If this height is 4, this height is 3, I will say overall height is 5 because 4 is there. So I will say 1 plus 4. This side height, let's say instead of 3, it was 6. So I will say overall height is 1 plus 6. 1 because of the root plus height of its children. Out of the children, whoever has height of the left subtree and right subtree, whatever is there. So my overall height becomes 1 plus higher height out of left subtree and right subtree, higher height out of left height and right height. So left height can be computed and similarly right height can be computed. So this will be the recursive definition. Stopping criteria. Obviously, if root is null, null means how much is the height? Null means height is 0 because root is at level 1. If root doesn't exist, what is height? Obviously 0. So height will be 0. So you will be returning null or 0 in that case. So effectively, now I can easily do the coding straight away by doing this particular logic. Effectively, how that will work? Effectively, it will give from 30, it will go to 40. So when it is trying to calculate height for 40, it will further go to 50. It will also go to 60. When it comes to 60, it will further go to 70. 70, it will further go to both sides. Both sides will say, this side's tree height is 0. This side's tree height is 0. So if both sides have height 0, 70's height becomes 1. 1 plus 0. 60's height becomes 1 plus left sub height, that is 1. Right height is 0. So it will become 1 plus 1. 1 second 1 coming from here. This becomes a 2. 440. This side height will come as 1. This side height has come 2. So 40's height will become 1 plus 2, that is a 3. Similarly, this height from the left side becomes a 3 plus 1, 4. Other side could come something and we will calculate like this. So this is the way your height can be done. I'm not writing code for this. I'm sure you can easily write for that. Let's say another operation. Search for a value and return its node pointer. So I will say, I want to search for a val and return its node pointer. Means if out of the tree, let's say I'm trying to search for 40, then this pointer to be returned. So in case of a search, I want the node pointer to be returned corresponding to 40. This return. If the value doesn't exist, null should be returned because I am returning pointer. So if the value does not exist, return null. Again, so that means effectively my function will be node star search, and within search what I need? I will need one root, obviously. And what else? The value to be searched. Obviously, recursion applicable or not? Yes, I can easily see. Let's say I am here 30. If I am searching for 30, obviously it will be found. If I am searching for something else than 30, it could be existing into left subtree. It could be existing into right subtree. If it exists into left subtree or right subtree, it is found. If it doesn't exist here, so search can be recursively called here. Search can be recursively called here if it was non-30, and otherwise I will say fine, done. So recursion useful, recursive definition. So definition will mean what? First of all, if root is not null, only then recursion needed. So if I'll say definition will mean if I have to go recursively, then what? So I will think of some if. Search into the left subtree. Search in right subtree. Obviously, if found, one of them will return not null because my node star being returned. So I can say left node or left side, left S or left N, left search, let's say left S. And similarly, I can say left search, SRCH equal to this. And similarly, I can say right search equal to this. One of this will be not null. Both will never be, obviously. And if it is not null, the element is found, otherwise not found. So, but this is only when recursion needed. There could be stopping criteria now slightly more. Of course, if root is null, that is stopping criteria 1. What is guarantee? If root is null, element not found, return null. But now there can be another stopping criteria also. What is that? If I was searching for 30 itself, so 30 was being searched. The data itself, root's data, was equal to the var. Then also no recursion needed, work is done. So you will be having the return, what you want to return, node pointer, node 230. So you will have effectively your root being returned. Now recursion will be applicable. So you will find left search. You will do right search. And based on that, you will have something to be returned. If both are null, obviously you will be returning null. If one of them is not null, then accordingly you will be returning the corresponding node because the call to the search will return the correct node from that particular node pointer from that particular call. So this will become implementation overall. So this can become your overall searching also. Not a difficult. I hope this is now much more easier the way we have discussed. Just taking 2 minutes on few more operations. For example, I want to say count leaf nodes. So count leaf nodes. Leaf node means if the node doesn't have any child, terminal nodes. So no left or right subtree, no left and right child. No left, no right child exist. Leaf means obviously this. Leaf is equal to this. How to do that? So obviously it will be int count leaf. So recursive definition, count from the left side, count leaf in the left, count leaf from the right. So both will tell how many total leaf nodes are there in both sides. I have assumed that recursion means a tree existed. So my total leaves are how many? Add these two. These are the total leaves. So that will be the simple logic. And of course, stopping criteria will mean if root is null, obviously count is 0. But if root had no left and right child, then it will become leaf. Otherwise, it could be there. So that can be additional point, which you must check. Because at some point, you must be able to tell when it is a leaf. So it is a leaf when this node exists, but its children don't exist. Leaf means node exists, and it has no left and right child. So this thing will be used to check for leaf presence as stopping criteria. And leaf presence obviously means no further recursion needed, and null also can be there. So both will be the stopping criteria in this case. Count non-leaf, I will leave it to you and think in these terms. But remember, never use the global variables or static variables to do this. You have to do all these programming where the calculations are done via recursion only. In online solutions or somewhere, you might get easier solutions using global or static variables, but don't use these. Your practice must be without these global or static variables. So coming towards the end, I will say now I have two more difficult or two better operations. So good students should be able to think in those terms. I'm telling you the operations to be thought. Average students might not be able to think. I will say first is whether two trees are equal or not. Equality of two trees. You have two trees existing. You want to check whether they are equal or not. So that obviously means I will have an equal function which will be supplied two parameters. One is root 1. Another will be obviously root 2. And now you have to tell whether both trees are equal or not. Return 1 if equal and 0 if not equal. Is recursion applicable? Means if I find the equality of the left side and equality of the right side, is it useful? Yes. So what will be the recursive definition? I say equality of two trees now requires what? If tree exists, when I will say equal, I need all of following to be true, because there are multiple conditions to be happening. What? Roots data are equal. That becomes that roots are equal. Only root compare. For example, I say I have one tree here 30. I have another tree here 30. This is root 2. So I will always focus on the current node. Remember, that is my way of solving the problem. Focus on the current node and assume the whole left subtree and right subtree. as a single unit. As a single unit. Don't assume that it has so many things internally. So equality means one. Roots are equal. If not equal, straight away they are not equal. But only root equality doesn't mean that they are equal. Root also should be equal. Left subtree should be equal to the corresponding left subtree. They should be equal to each other. So the second condition means left subtree of both are equal. Roots are equal or not, it is non-recursive straight away. These are equal or not, obviously means recursive. Recursion is visible here, I can easily see. And similarly, right subtree to be equal, that also means recursion. So these two are recursive goals. This is third step. All three to be true, then only it is true. If one of them is false, obviously false. Stopping criteria, obviously you can think. So think of stopping criteria. If both are equal, can I conclude something? You can guaranteedly tell yes. If both are null, sorry. If both are null, you can guaranteedly tell whether they are equal or not. Both are null, so they are equal. One of them is null and other is not. If one of them is null and other is not null, obviously again you can conclude guaranteedly it is not equal. If both are not null, only then recursion will be needed. Then you have all three conditions to be checked. So whatever we have written above, all three conditions will be checked. So having told that, I think now you can try this one also, and hopefully you will be able to implement this also without much of a difficulty. Coming finally to another more important or another difficult, slightly difficult operation, I say find mirror image of a tree. Find means effectively, I mean generate. So I want to generate mirror image of a binary tree. Means if this was for 30, let's say this was 40, say this was 50, this was 80, this was, let's say, 90, then it's a mirror image means effectively this will become 30, 80 will become its left child. Earlier 90 was 80's right child, but now 90 will become its left child. 40 will become its right child. 40's node will become 50 as a right child. 50 had, let's say, right child as a 60. So 50's left child will become now 60 and like that. So how to do? I will say solution has to be, think that left subtree is 1 unit, right subtree is 1 unit, and now you have effectively 30. This side is some unit 1, which is recursively solvable. This side you have unit 2, which is recursively solvable. Effectively, this side you should become 30's. Left side should become unit 2. 30's left side should become unit 1. And having said that, effectively my mirror image is ready. So I don't write further. You should try this. And of course, I have said that equality and relative mirror image, these two are more standard operations. So the good students should be able to code directly, and good students must solve it. Just winding up towards the logic now, final operation. Again, not difficult, but you have not thought. I say find all ancestors of a given node. For example, I say I have given you 60. Now, corresponding to 60, if 60 is here, 60's ancestor means the Purvaj in Hindi. So those who don't understand English or might not have heard of this word, so that means Purvaj, the parents, grandparents. So 40's parent is 50, 50's parent is 40, 40's parent is 30, and 30 has no further grandparent or no further ancestor. I want, so for 60, my parents should be listed in that order, 50, then 40, then 30. I want this output. These are my ancestors in this order. How to do that? 60, I will say search for 60. That you can easily do. We have already written the function. Once you searched for 60, this pointer is available to you. Now, you have reached to node 60 PTR available to you. But you want PTR's parent. How to get that? You have no way to go from 50 to the parent. So maybe you have to write a loop, check for presence, whose child is 60, keep on finding that, and only then you find 50. But I don't stop at 50. Now I say find whose child is 50, again recursively or iteratively find, and who is the child, whose child is 50, again you will get 40. Same process to be repeated. So if you do now, it will be a time consuming and slow process. The algorithm can be made recursively, can be made, and it will be slow process. It can be fastened by storing a parent into each node. So I say the same thing you can do by storing a parent in each node. If you are able to do that, things will become easy. Meaning, if I have created 30, when I created 40, I say 40's parent is 30. This link also stored. You added 80 this side. I will say 80's parent is 30. 30's parent will be null because it is root. So root's parent will be obviously null. But every other node, if I had, let's say 50 here, I had 60 here. So this parent link being maintained. This side I had 70. So I will say 70's link like this maintained. 80 had, let's say 90. 90's link also maintained. 90 has left child 100, parent maintained. So for every node, parent is also stored. Means during creation, you have to have additional linking, not only one left or right linking, additional linking to be done for every node. Or to be done for every node, for whatever nodes you have done, for all of those nodes, this additional linking must be ensured. For example, earlier you said roots arrow left equal to create. That is fine. But you have maintained only one side link. Now you want this link also to be maintained. But for maintaining this link, once you create this node, once this malloc is done, only then your root will be possible to be linked, because only then your parent link will be available. And you, for this linking, you will need root node also. So effectively, you will require some extra parameter, and the way we have discussed earlier also, that extra parameter will be needed to be past here and think in that terms. What does that mean? Effectively, that means the node structure will change. Earlier, I had in the node, I said was I had a data. Along with data, I had left pointer. I had right pointer. But now I will also store a parent pointer. This is additional. So this will require additional space. And it is effectively additional space complexity. Because for n nodes, order of n additional nodes are needed or additional pointers are needed. For n nodes, n extra parents are stored, so it becomes additional space complexity. It's not just one or two variables extra. For n nodes, if n is 1 lakh, I will have 1 lakh extra memory needed for parent pointers. So effectively, we call such things as a time versus space trade-off. If I want to improve the time complexity, that will require many a times extra space to improve time complexity. So if I want to reduce time complexity, I will probably require sometimes extra space complexity. This is what we call that this is always a trade-off. If you try to reduce space, your time requirements will increase. If you try to improve your time, your space requirements increase. For example, in this situation, for ancestors, this was a problem. Others we could easily do without that requirement. Ancestors find. But if it was ready, once I am to the PTR node, say PTR points to node with 60 value, effectively, I have to do nothing. I have to just go on going to, let's say, while parent, say PAR not equal to null, you can just keep on having the parent found. So parent means what? Parent will be always PTR arrow parent. I am on the 60 node. PTR's parent points to 50. I even can just keep on doing the printf, the parent's data to be printed and parent to be again found. So I will say parent equal to current parent. Further, it's above parent. That's it. Mint, I was on 60. This is my PTR. PTR's parent is this. So I will have a PAR pointer created and PTR arrow parent takes me to this node. And now PAR is ready. So print 50 and then again apply this. This further takes me to 40. Print 40, again apply this. This further takes me to 30. Print 30 and again apply this. It takes me to null and null. I will stop and work done. So this is the way I can do this trade-off also. So having said that, now I think I will stop. So as a homework, I will say you must practice all these operations which we have just discussed. So effectively for parent linking, we have already discussed the create 3 where we needed some parameters that you could do. So I'll say find max and count you have already done. So count leaf nodes, count non-leaf, but don't use any static variable, don't use any call by reference or some kind of those things. Use return type and no global, no static variables. Use all recursion to do that work effectively. Recursion should return type to be used to contribute for this. So count leaf, count non-leaf nodes. Similarly, I will say find height, search. This you should be able to do. Good students, for them, I will say you should be able to also do the equality. The next being mirror image. And then ancestors. For ancestors, obviously, additional changes into your create also needed. And in order to confirm that, you can verify this by printing for a lot of this. Test it well for various nodes. Because here you are likely to make certain mistakes. If you are likely to make mistakes, so you must test it for various situations and normal cases versus special cases also. So with this, I think I will stop and wishing you a great success and try to do all this. This will give you a great learning and you will be able to really visualize. The thumb rule is always you should be able to visualize the recursions working. That you must ensure that you are able to do that. I think I have stopped the screen. So